Okay, welcome back. Today we're going to be looking at Unit 2 of the BJC curriculum. And Unit 2 is all about abstraction. Okay. Now, let me frame this properly. Abstraction is one of the big ideas from the College Board. Okay. It is not quite the case that every big idea gets its own unit in this curriculum. Some of them are just kind of scattered throughout. But this is one place where we're just really going to hammer this and try to get the students to understand abstraction. Okay. So let me start with this. Abstraction is actually, it's in very many different fields, right? Perhaps I should say in every single field. So one of the things that might come to mind is right here. This is actually an abstract sculpture. You can see it in Daly Plaza in Chicago, and it's quite impressive. It's a Picasso sculpture right there in the heart of the city. I've looked at it. I love it. I absolutely love it. I have no clue what it is. Okay. Picasso is an abstract painter, and that's kind of what he means. Sometimes you don't quite see what he's trying to do. Okay, there are two different stories as to what this abstract sculpture represents. One of those is that it was inspired by the girlfriend of another artist, and this artist came to Picasso's studio delivering something, chairs, paints, whatever, we don't know. The point was that the girlfriend would accompany this other artist in his deliveries, and Picasso met her and went, "Oh my God, you have just the perfect, figure," which then, of course, he proceeded to not replicate exactly because he was an abstract artist. And one thing that we know about her is that she had a very high ponytail, long ponytail, and so maybe that's what he's doing. In fact, he painted her many times. At the time, a lot of people thought that he was actually painting Brigitte Bardot, who was the famous French movie star, but it wasn't her. It was actually this girl whose name I don't even know. So it's possible that that was the inspiration for this work of art. Now, another inspiration of this giving is that it's actually this dog right here, okay? Or at least this breed of dog. And you can kind of see the long, yeah, okay, I see. Maybe that's what Picasso saw. And so he abstracted that dog into that picture. So what am I talking about? But in the process of abstraction, what Picasso, in this case, or some other artist might do, is to really focus on the important things, right? These are the important things about this person's face, this person's shape, and there we have an absolutely beautiful sculpture. Okay, so that's one thing, right? Instead of actually taking a picture, right, that captures all the details, right, we're going to focus on the ones that are important, that are essential, right, and that's abstract art. Okay, something else that that you might see from that is, by focusing on the things that are important, you actually help somebody else see what is important and what they should learn. So look at this guy here. This is a frog. Right? What happens when you dissect a frog, like many of your students may have had the opportunity to do. And let me tell you that this picture actually shows you the important things inside the frog, lungs, that kind of stuff. Let me also assure you that it is a lot cleaner than the actual frog dissection experiment that they may have to do. So again, abstraction, right? We want to show the important details and kind of hide or blur the other details so that we know what to learn, right? From frog dissection, you might simply learn that, right? This is horrible. I never want to be a doctor. But from this picture, you might actually learn, oh, these are the things that frogs have inside of them. Okay. So again, that's abstraction. Something else that you might do is sometimes it's just not feasible to work with the quote real thing. Instead, we work with an abstract model. And that's a technical term, okay? It's a kind of scientific term, a model of it. So what am I talking about? I was actually stunned recently because I saw a picture of Jupiter and the 4 Galilean moons. Okay? The reason I was stunned was because this picture also had kind of a picture of the moon off on the other side. I never realized just how large the extent of the moons were, okay? And I'm an amateur astronomer. I've looked at them through a telescope many times, and it just never clicked on me what the scope of the moons was compared to another object like our moon, okay? I've had that same experience with even galaxies. It's like, look at this thing, it's like, oh, it's beautiful, it's gorgeous, and then later I learn, what? It's actually the size of 2 full, how can it be, right? But that's, again, just has to do with what I'm focusing at a particular time, I'm missing some of the big picture, okay? So let's say that you want to help your students understand the scale of the solar system. So let's build a model of the solar system, right? And this is done in elementary schools throughout the country. So we have a big sun, right? And then we have a tiny little Mercury, you know, and then a somewhat bigger Venus, and then the Earth and Mars and so on, right? And we put all the pieces. If your sun is actually of, say, the size of a basketball, okay, the solar system will not fit in your classroom. Okay, there's simply no way to have that scale of how big are these objects compared to how far apart are these objects, and keep that in the same scale, and you know, actually do it in any kind of reasonable space, right? If you want to keep it inside your classroom, you may not be able to see the planets because they're actually subatomic, okay? So darn, right? How can I show you something that's real? Actually, you need like a huge space. And for example, at Cornell University, they have that, and it occupies a significant part of the campus, except you don't notice because it's just like a ball here, a ball there, and so on. But wow, right? That's the power of abstraction. What do I want you to learn? I want you to learn that there's, you know, 8 planets, 9, whatever, okay? No problems, right? I can actually show you a model that shows the planets, right? They're actually way too big within their orbits, but I'm trying to show you what's important, okay? Oh, do I want you to learn about how far apart they are? I'll show you the orbits as circles, right? And show you all the orbits, and then you don't see any of the planets, right? You know, they're little dots. You don't even bother drawing them. You're just drawing the orbit that they travel through. Again, abstraction, okay? So when you have abstraction, one of the things that you can really do is guide people's eyes towards this is important, that isn't, right? You might actually be able to say all of these things, all mammals, for example, right? There's an abstraction. All mammals have the same properties, okay? So now you've simultaneously talked about cats and dogs and humans and apes and all sorts of things, right? And of course they have differences, right? You know, so you can actually help people learn about that. That's another value of abstraction. Now let's bring this to computers. What does abstraction mean in computers? First place I want you to know is that we have blocks, right? Other languages call them procedures, but we have blocks that abstract a bunch of code. I don't need to know that code. I simply call the block and it does whatever I asked it to do, okay? We also have abstraction in data structures. For example, I might have a list of students, right? I don't need to know each individual student. They're just a bunch of students that are kept in a list. That gives me abstraction. It's not Mary and Sally and John and, right? You know, it's a list of students. I notice that abstraction. I can't even name them anymore, okay? All right, so let's talk about the first lab that they have to do. First lab, let's improve on a game by using variables. What they're really learning about is about local variables, and these are variables that are valid only in a single section of code, right? They're local to that code. And global variables that are available throughout the entire code, okay? So that's important, right? By the way, something else they learn when they're doing this lab, they learn to go to one of their previous labs and take something out of it, export it, and then import it into their current lab. This is really super cool, right? Yeah, it's great. What does it have to do with abstraction? I mean, we're talking about variables. Let me tell you this, a variable is not an abstraction. The College Board is very clear on that, okay? And it has to be very clear on that because there's a lot of computer science PhDs at universities that will tell you, oh, you're using a variable? The variable is called temp, and it represents the temperature in the room. Abstraction happened. The College Board says, no, okay, that doesn't count. Okay, fine. But you can see how abstraction really goes through everything. So let's take a look at this to kind of really make it clear. What does this have to do with abstractions? I have a variable or a list maybe that has a whole bunch of values, okay? Well, here's the idea. We're going to have a bit of code that does something, okay? And then we're going to advise that code by giving it a data structure. And what's going to be nice is that the result is going to be this beautiful behavior, right? In this case, we're writing a letter, right? A nice letter. This is an A, and notice it's got, you know, like it's a solid letter, okay? But it's not the code that knows how to write a letter A. It's actually this list, okay? So what we have here is a list of, hey, notice that each element of this list is actually a list itself, right? It's a list of lists. And each one of the inner lists has 2 elements that are numbers. Those two elements are called coordinates. Okay, and what we have is list of minus 50 comma 20. Those are the coordinates of a point in the xy plane. Okay, and every point has two numbers. I put them in a list because a list lets me collect more than one thing at a time, right? And I need lots of points because if I have all the points that represent, for example, the vertices of a polynomial, then I can have a very simple program that starts at one point, goes to the next one, goes to the next one, goes to the next one, and so on, and draws whatever the points say. Where is the intelligence? It's in the list. Okay? The code is actually pretty straightforward. Start here, go to there, go to there, go to there, go to there. Okay? And so what have they taught you, right? What are they really trying to get across? Abstraction, right? The list is an abstraction of the letter A. Okay? That actually stores the important information about the letter A. Where are those corner points? Okay? So that I can recreate the letter at will. Something else that is done here pretty quickly, abstract data types. Okay? Now, abstract data types is a technical term in computer science. The way that this curriculum introduces it is not quite the same as what is usually meant, but the ideas are pretty close. Okay? What we're doing here is, for example, we're going to build a point. Right? Remember how we had it as just a list of two things? That gets confusing. A list of two things, yeah, I know that that's a point. A list of two things, yeah, that's a list of points. Let's just make them points instead of quote lists, right? So right here, what we'll do is we'll write a block called point that takes two values, the x and the y coordinate, and then returns a point. Okay, between you and me, it's just a list of two things, right? But it's abstracted into something that is called a point, right? That's another step in abstraction, okay? And then we're going to write two other functions, one called x coordinate of, you give it a point and it tells you the x coordinate, y coordinate of, you give it a point, it gives you the y coordinate, right? So if you look at those three things together, point, x coordinate of, y coordinate of, those three blocks make up an abstract data type, okay? We might call them something else in other languages, and they're called classes, they're called records. This is what we have. Okay, in Java, this would be kind of the main thing that we would talk about. Okay, so I have a bunch of points. Okay, one of the things this lab introduces is, you know how actually knowing the points, that's the intelligent part. It's not the code, right? The intelligence is in having this list of points. Ooh, getting that list of points is actually hard, right? And they actually show you how hard it is by telling you, go ahead and do an A. Go right ahead. Let's do an F now, right? And it's actually hard. You have to draw it and get it right. So their next step is, why don't we write a program that captures those? So what do we mean by that? Look at the mouse, right? Let the user actually move the mouse. Click. Ah, okay. That's the corner. Okay, click, click, click. And you can actually capture then where the points are supposed to be. That's beautiful, right? Incidentally, this is a direct tie into things like motion capture in movies, right? Where you might have a monster on screen that's a great CGI monster, but there's an actor that's moving around with all sorts of dots attached to them so that a camera can see how they move, and that directs the movement of the CGI monster. Boom, exactly like this. Also, machine learning. Okay. Because in machine learning, part of what it's doing is trying to find some data structure, like a list of points, okay, that is actually hard for humans to write down, but that the machine can learn by observing, right, by having lots of examples. So there are kind of two, one not very subtle, one fairly subtle connection between more advanced computer science and what they're seeing. Okay. Now, the other thing that this lab shows them is how to create those set of points in a context. And here is kind of a cherry picking place. Remember we have this polygon drawing routine? It knows how to draw a polygon. Well, the way that it did it was it started here, and then it moved there, and then it moved there, and then it moved there, and so on, right? But what if instead of moving, it simply told us, here's one corner, here's the vertex, there's the point for one corner, here's the point for the next corner, the next corner, the next corner, and so on. And then it just returned that list of points. Then we could run that through a little code that draws the list of points, and you see a beautiful polygon, okay? So that's part of what this lab does. Okay, let's move on to the third lab in here. Okay, and the third lab in here is all about, quote, making decisions. Okay, so the first thing that we do is we're going to introduce a new built-in data type. Okay, we've already introduced some numbers, strings. Okay, and we've also introduced abstract data types like point. polygon, right? But here we're going to introduce one of the new built-in data points, built-in data types that comes with Snap. And it is a Boolean, or also called a predicate. It is just simply either true or false, right? So it's like the result of a comparison, right? So that's great. I can now have, and if you look at hello here, you can see that above a certain threshold is red, below a certain threshold is blue. So that threshold is like a Boolean. Am I above or below? True or false? True or false, right? So that's actually shown here in a very graphic way, okay? Something else that's kind of introduced here is a type of block called a reporter block. And what it does is it returns a value. Okay? Now, when the value that it returns is a Boolean, then we call reporter blocks predicates. That's just a convention. A predicate is a block that returns either true or false. Okay? So that's what we have here. Okay? That's lab 3. The very next step is absolutely huge. Okay? So here's kind of the big jump. Okay? We're going to apply a single predicate to all the elements of a list. Right? So let me just give you one quick example. Let's say that I have a list of numbers, integers, right? 1, 5, 12, 6, just a list of numbers. I would like to see which ones of those numbers are even. Right? So I could apply one predicate, even. Are you even? Okay, that's a predicate. I could apply it to each one of those. So 1, are you even? No. 3, are you even? No. 6, are you even? Yes, and so on, right? And so I get back a list that says true, true, false, true, whatever, okay? Just simply asking, is that element of the original list odd or even? Yes, no, yes, no, okay? So that is kind of a big step, okay? I got to stop. Sorry. I need to start this slide again.
Sure.
Okay? Mostly because I described the wrong major step.
No
That
worries.
comes in lab 3.
Okay. Yeah, feel free to
I'm sorry, unit 3.
take breaks when you need them too.
Yeah, I was doing map instead of keep. Then I saw wrong one. Okay. So let's move on to lab 3. You know, we're talking about making decisions using predicates. We've seen what a predicate is. We've seen blocks that return true or false. This next step is huge. Okay. So what we're going to do is we're going to use this predicate to kind of sieve or filter through an entire list. So here's the idea. Let's say that I have a list of numbers, right? And let's make our life easier. Let's say the numbers are 1, 2, 3, 4, 5, up to 10. Yeah, it's just a list of 10 numbers. Okay. Now, one of my predicates could be even. Are you even? And if I say 1, are you even? It says false, right? 2, are you even? True. 3, are you even? False, and so on, right? Okay, so the big step is to think of a single block that can kind of look at a predicate and look at a list and return all of the elements of that list that make that predicate true. So if I say, keep all the elements of this list, 1, 2, 3, 4, 5, up to 10, that are even, it will come back with the list, 2, 4, 6, 8, 10. Okay. Those are all the elements that are even. Beautiful, right? I would like to actually be able to find all the movie stars that have made more than 10 movies. Okay, so give me a whole bunch of movie stars in a list, right? And the number of movies they made. And I'll go through it and say, have you made more than 10? Yes, okay, I'll keep you. Have you made, no, I won't keep you. And so on, right? And I end up with a shorter list, all the ones that have made more than 10 movies. That's what this block is. This is a new block that they're going to learn about. Keep items such that, and then the predicate, the test, from some big list, okay? And it returns all the elements of that list that meet that predicate. This particular example here, it says where letter 1 of blank, I'll talk about that, is equal to V, right? Blank. What is the blank? That is the element of the list that I'm considering testing. Remember, are you even? Even blank, right? We'll take an element of the list and put it there to test. Yes, I'll keep it. No, I won't keep it, right? That's what this thing does, okay? Very important to know, it returns a new list, right? It just creates a new list that has everything that passes. And I'm just going to tell you right now that this is one of the big 3 operations on lists, okay? We'll talk about the other 2 in future units, okay? This really introduces, again, this is kind of the BJC philosophy. We introduce complex computer science ideas, but we don't call them complex computer science ideas because then the students say, oh, I probably can't learn that. Not true. This is just blocks. You can learn it. Okay. So the thing that it kind of subtly introduces, I have an argument here. Keep items such that an argument goes there, right? And what actually goes there is a block. It's not the value of a block. Like it's not like I put in there 2 plus 3 and the argument that goes there is 5. No, no, no. It has a blank. It's that blank again, okay? That keeps it from being able to compute right now because you don't know what the input is. Are you even? Who are we talking about? 2 or 3? Until I know which number we're talking about, I can't answer the question. Even? Right? So that blank is important, right? That will get filled in by each element from the list later, right? But in the meantime, what I can say is that it is a kind of computation that's in the middle. It can't progress because it doesn't know what we're asking about, okay? Those blocks that have an open parameter, you know what? They're actually called functions. It's like f of x, right? F of x is 2x. That means that if you give me x, you say 4, then I can tell you the answer, 8, right? If you give me 5, I'll tell you 10, right? If you don't give me something, I tell you, I don't know, right? I'm waiting. There's that blank. F of blank is 2 times whatever you gave me, right? We see those in algebra. So in this case, we're actually making a connection, subtle though it may be, and you are welcome to make it totally overt, okay, in your classroom. We're making a connection between functions that they might learn in Algebra 1 or pre-algebra and programming, in this case, blocks that have a blank. All right. Next lab that we do in this unit is about robots in a maze, right? Oh my God, does the AP CSP exam love robots in a maze. They will have lots of examples of the robot starts here. It executes the following instructions. Where does it end up and in which direction is it looking? A, B, C, D, or E, okay? So your students are just gonna have to be able to think like that. Also, the robot is here. It wants to be over there. Which one of these programs will get the robot from here to there, right? So this is actually what they'll experiment with in this lab. We'll give them lots of mazes, right? And then we'll say, oh, write a program that when you put the robot in this location and you say go, it will happily navigate that maze and get to the end, okay? This is also a great opportunity to witness abstraction. Remember, this is the abstraction unit, okay? So where is the abstraction? There is a block called draw maze that takes in a maze as an argument, right? Abstraction just happened, right? That is kind of a, quote, dumb block, right? The intelligence is not in the code. The intelligence is in the maze that tells it which squares are occupied, which are not, okay? So it's a good example of abstraction. The code is abstracted. It's a block, right, of code that draws the maze. It's also a good example of abstraction from the data perspective. The code doesn't have to be all that smart because the data tells it the information it needs to know, right? So all of that is good. And of course, they encourage you, in fact, they ask you to open up the definition of the block so you can see how it happens inside, okay? Great, great lesson. All right, again, I want to talk about the real computer science that your students are learning, okay? Number 1, this is the goal, right? Abstraction, right? They know the blocks can abstract some code, right? Once you have a block called draw polygon, you do not have to think about how polygons are drawn again. That's the point of abstraction. You hid those details. You only show what's important. What's important about a polygon? How many sides are we talking about? How big are those sides? That's it. That's the abstraction. You can also abstract in data structures, right? So list of vertices abstracts a shape, like a letter, okay? That's what this section is all about. You're gonna learn in this particular unit about using blocks as arguments to other blocks, okay? Like I said, this is a mind bender because I'm not sending a number as an argument to a block. I'm not telling it, draw a polygon with 3 sides. 3, that's the argument, right? I'm actually passing the draw polygon with number of sides as an argument to something else, right? That is so amazingly powerful. It's called higher order programming. We're just kind of showing it as, yeah, see how easy it is, okay? I'm re-emphasizing this, but blocks that are actually functions, like f of x, those are blocks without blank, okay? And we'll learn one of the major list operations, abstract list operations, which is called keep. This major list operation has other names. It's also known as filter. Filter this list for the things that pass this test, okay? It's also known as select. And if you know databases, for example, the database language, which is called SQL or SQL, the first keyword is select. Select these things from this list, where, meet this condition. So, you know, selection is actually a concept in a lot of different places. And here we met it in this unit, Unit 2. Okay, as always, there is a discussion lab. In this case, the discussion lab is about copyright. Okay. Now, again, copyright is one of those issues that it's important, is multifaceted. Okay. So, for instance, Shakespeare was able to write Hamlet, not a bad play, and a lot of the plot actually was based on some previous stories that were set. Okay. And he had no problems doing that. Nobody actually had any problems doing that. In the time of the Greeks, you would have great plays that competed against each other. What is the best play of the year? Kind of like the Oscars. And people would go and see them, right? And the stories in those plays were stories that the people already knew. It's like, yeah, we're going to hear the story of Orestes again. Awesome, right? What was interesting was how they were said. So there was no kind of concept of, hey, wait a minute. Or, what are you doing, Aeschylus? You know, somebody already wrote this. You cannot do this again. No. That's the way the world worked, okay? So that's how it was, right? Today, I can't just say, you know what, Harry Potter. I can write great stories about Harry Potter and just go off and run with that idea, because that'd be violating the copyright of J.K. Rowling's, right? So copyright is a relatively new concept, meaning it wasn't around in Shakespeare's time. But it's an important concept, right? Because how else am I going to reward somebody like J.K. Rowling for writing such delightful stories? My personal biases are that students would be somewhat, shall we say, insensitive about copyright. Of course I want to stream that music without paying for it. You know, why is there even a question, right? Some of them I thought might even be defensive, such as, but you know, they're getting free advertising. They should thank me for streaming their music for free, right? I've actually found that they have much more nuanced feelings about this. So it's really, really kind of cool. Now, the lab also asked them to consider deeper questions about copyright, such as, how do computers affect copyright? Okay. When I started teaching, and I guess I'm showing my gray hair here, but when I started teaching, I was actually rational as to how often I could use the copy machine. I had to use something called a mimeograph that I hope none of you ever have direct experience with, okay? But yeah, so actually copying an entire book would have been a just impossibility, right? I mean, what am I going to do? Stand there and page per page? No, it's not going to happen, right? In the day of computers, I just simply give you the PDF file. Here, you know, I have the PDF. Actually, I have the PDF for Blown to Bits, right, which is the book that all of these discussions come from. I have the PDF file for that, so I can just share it with all of my closest friends, you know, 100,000, 200,000. The authors of Blown to Bits actually make their book available for free, so you can use it in your classroom without having to buy it. It's really kind of cool, okay? But the advent of computers clearly affects copyright, because now copying is so easy, okay? And how about going the other way? Can we use computers to enforce copyright, okay? Well, maybe. And there are things such as, I can't just take my DVD player and route it through some cable that goes to a computer, right? Because the DVD player talks to the device on the other end and says, what kind of device are you? Oh, you're one of the TVs that I know about. Here you go ahead and play this, right? So that actually uses encryption, pretty advanced technology, entirely built to make sure that you cannot copy DVDs, right? So that's the state of the world. Lots of discussion points in here, and that's what you need to do with your students in your classroom.